Today we will discuss the thermodynamic properties in terms of partition function, and we will also try to derive internal energy in terms of partition function, entropy, enthalpy, specific heat at constant volume, and also pressure, Helmholtz function and Gibbs function. First, we will take the internal energy here. The internal energy U of a system consisting of, we have to consider a system consisting of n independent particles. These particles can be atoms or molecules. And this internal energy of the system consisting of these n independent particles will be equal to the sum of the energies of the individual particles. Suppose we will also consider that these n particles, that means n independent particles, they are distributed among several energy levels, or you can say states. Suppose the number of particles n0, suppose this is in energy E0, similarly n1 in E1, n2 E2, and so on up to Ni. You can say, and similarly for energy it will be simply EI. Now we know this internal energy, it is basically the sum of these energies, that means n0 E0 plus n1 E1 plus n2 E2 plus so on up to Ni EI. Or we can simply write this in a very compact form, that means we can simply write it as summation of Ni EI. But we also know from Boltzmann Einstein or Maxwell-Boltzmann distribution that number of particles in the ith state, and this is total number of particles is equal to Gi, the degeneracy, into e raised power minus Ei upon kT. Here Ei is the energy of the ith particle, K is the Boltzmann constant, and T is temperature, divided by summation of Gi into e raised power minus Ei upon kT. So this will be simply equal to, we know the denominator term, that means this term is basically equal to the partition function. So we can simply write this relation as Gi e raised power minus Ei upon kT divided by Q, where Q is simply the partition function. If we consider a case where this degeneracy is equal to 1, or you can say non-degenerate, then this relation can be also written as e raised power, and this is simply Ni, so we can take this n to this side, so we will simply multiply it. This is n is the total number of particles, you can say here, minus Ei upon kT whole divided by simply the partition function. That means we got this Ni here, value of Ni. So if this is equation number 1, this is 2, this will be 3, 4, and this will be 5. We will use equation 5 in simply 4. So equation 5 in 4, internal energy U can be written as summation Ei n upon partition function into e raised power minus Ei upon kT. So this can also be written as, if we simply take Ei here, this n upon q outside, we can write n upon q will be summation e raised power minus, or this will be first here Ei, it will be Ei into e raised power minus Ei upon kT Ei. So partition function is basically equal to summation Ei e raised power minus Ei upon kT if here gi, that means degeneracy is simply equal to 1. So we can simply differentiate this relation. That means we can write with respect to temperature dq upon dt will be equal to summation e raised power minus ei upon kt into differential of function. That means it will be equal to minus ei upon kt. So this will be simply equal to, when you differentiate this one, it will be equal to ei upon k t square into summation of e raised power minus ei upon kt. So that means we got this part, that means summation ei e raised power minus ei upon kt will be equal to, this will basically equal to dq upon dt. We are simply taking this part here, this side, so it will be simply equal to dq upon dt into kt square. So we can use this value and put it into the internal energy, that means U, that means it will be equal to N upon Q, and into in place of summation e raised power ei into e raised power minus ei upon kt, this part we will introduce this, that means dq upon dt into kt square. Here k is simply Boltzmann constant, so this can also be written as n k t square t. Here it is differential of q divided by q, this can also be written as b ln of q divided by dt. So this is very simple relation, but we know from this relation that this nk, if we take the total number of molecules into Avogadro, this Boltzmann's constant, it will be equal to number of moles into gas constant. So we can write internal energy then nr t square and d ln of q upon dt. So this is basically the relation of internal energy in terms of partition function. So also now we can simply derive the heat capacity relation also from this simple internal energy relation. That means heat capacity, but at constant volume, we know this is related to the internal energy by change in internal energy with respect to temperature but keeping the volume constant. We know this relation from thermodynamics. So if for Also we will take n is equal to 1, that means 1 mole of system. We have already got this internal energy. We will simply put the value here and differentiate it with respect to